Hello, anybody's there? Let us start today's work. Uh, I hope that you will join soon. Last month, in the last class, I have discussed the theoretical vapor compression cycle with dry saturated vapor after compression. This means after the compression, the vapor is dry, there is no moisture is present in terms of water, in the form of water, and it is completely saturated, means it is carried with the exact full amount of vapor for the under the given under the given pressure itself. So first we have to do the we have to compare a VS, a TS temperature entropy and pressure enthalpy diagram. Next, what we have done, the vapor refrigeration at low pressure and micrometer is compressed isotrically to dry vapor shown by the vertical line on TS and on the curve 1, 2 on pH diagram, which means as 1 to 2, that's the line shows by the compression in TS is a vertical and straight line, and 1 to 2 is a curve in pressure enthalpy diagram, which represents the rise in temperature from 1 to 2 without any change in entropy. And as the point 2 is over the saturation line, it proves that under the action of the corresponding pressure, the point is vapor at the exit of the the compressor is totally saturated and totally dry. But at the point of point one, which is the point of entry of the compressor itself, it is not fully. It is in the wet region of the TS diagram. So it is in the wet region of the TS diagram. So it has a fraction of vapor and a fraction of liquid water itself. Now, and pressure itself is varying from 1 to 2, and enthalpy is increasing with the increase in pressure by the addition of work done. Enthalpy or the heat content or energy level, whatever mean the name, it can assign it will increase from 1 to 2. Now, and pressure is increasing from P1 to P2. Next, goes the condensation process at too high pressure. Just a minute. Next comes the condensation process. From 2 to 3 is the condensation process, starting from the point 2 on the dry saturated vapor line and finishing at the point 2 where wet saturated vapor line. Means condenser is high pressure and temperature. Here we are seeing the temperature remains T2 to T, temperature doesn't change. This isothermal change, the temperature remains T2 T2, which is equal to the T3 itself, and pressure itself remains same from 2 to pressure T2 to T3. It is not changing, which is equal, but enthalpy is reducing from 2 to 3, means the energy is released, the heat energy is released during the condensation process. So what happens here? Vapor is changed into liquid refrigerant. The vapor refrigerant from here or from here is totally compared into the liquid refrigerant itself. And it gives out this condenser gives out the latent heat to the outside surrounding condensation medium. Now, next comes the extraction process, that is starting from the point 3 and to the point 4, and 3 to the point 4 itself. So what is going on here? Here the temperature you see is dropping from T2, T2 to T2 or is equal to, which is equal to T3 to T4, which is equal to T4, T3, T1, which is the initial temperature at the time of entrance of the compressor itself. It falls from 3 to 4, and entropy to a certain extent is changing from 3 to 4 itself. But here is the case is there. Now, what is there is the important thing, the process of expansion by the throttling process itself. Now, here it is important to what is the process of expansion? It is important in one sense because it depends on each, a lot of things is depending on it. What is the process of expansion? One, it can be done by throttling process. And or it can be done by an expansion cylinder. Here, the throttling process is not isentropic. But expansion cylinder is isentropic. But throttling cycle, the pressure of expansion can be controlled. And flow rate can be controlled. Not pressure exactly. But expansion is isentropic, but it is much more expensive. And flow rate cannot be controlled. What is shown here, the if it's done by the expansion process, expansion cylinder process, then it becomes isentropic, means there is no transfer takes place. And T4 will come, so number 4 will come here at this point. So from if we used it, we will get if T4 will come to the process. So the process of evaporation will increase from, say, if it's T4 dash, so for 1 to 4 to 1 to 4 dash, can be from 1 to 4 and 1 to 4 dash. But which means higher amount of heat is being extracted during the evaporation process from the surrounding of the evaporator itself. But it makes one of the problems. This type of expansion cylinder supposed to be more expensive. This will be isentropic process, external work being expended in running the compressor and increase the refrigerating effect, which is if we use the expansion cylinder, it is refrigerating effect or more amount of heat will be extracted from the surroundings of the refrigerator itself. But this will increase the COP performance. COP will increase for that. The process will increase. But in the expansion cylinder, it's quite complicated and involves a greater amount of initial cost. First, it is not justified for this 10 is not high, but this 10 is not high enough to use an expensive cylinder. So generally we use that throttling valve, where flow can be controlled and to a certain extent pressure and temperature also controlled. But it's some amount of heat will lost in the throttling process, and pressure although remains more or less, this enthalpy remains more or less constant from 3 to 4, but pressure also reduces from P3 to P4. But let us go through. Always we are using the capillary small port hole tube in special expansion valve. Present use is expansion valve itself. Next comes the vaporizing process. Here, liquid vapor air mixture, liquid vapor mixture of the refrigerant at pressure T4 is equal to T1 and temperature T4 is equal to T1 is evaporated and changed into the vapor refrigerant at constant pressure and temperature. So what is we are doing here? This is the expansion process, evaporation process. It is evaporated from 0.2 to 0.4 and entropy is thus added, means entropy is increased from 4 to 1, means more heat is being added to the refrigerant itself. This heat is being used for the conversion of liquid refrigerant to vapor refrigerant, which is taken at the input of the cylinder itself, which is taken at the input of the compressor itself. So here, this 4:1 is the amount of heat which is used for as a latent heat of evaporation of the refrigerant, and at the same time, this amount of heat is being extracted from the surrounding of the evaporator itself, which is creating a refrigerating effect. So the 4:1 on TS line and pH diagram is the evaporation process. During the evaporation, high pressure absorbed latent heat of we just have told you, and generally from the medium can be air, is a free, it can be a free atmosphere inside the refrigerator or inside a air conditioned room. It can be water also, or it can also be brine water. Brine water is a salted water which has low low melting point or low vaporizing point, and it can be cooled whole system itself. But generally nowadays, total refrigerant is only used to make the refrigerating effect. So that this portion is defined written as RE, the process of vaporization up to point 1, which is the starting point, and that cycle is complete. What I have told you about the cycle, the process is always repeating, starting from 1, next operation from 1 to 2 is the one operation, from 2 it is next operation condenser, 3 to 4 expansion, and 4 to 1 again evaporation. So when 4th operation is complete, the initial point 1 is reached and it is repeating again. That's why it is called cycle of operation. Next comes now the refrigerating effect of the heat absorbed or extracted by liquid vapor refrigerant per kg of the refrigerant is given by RE. This refrigerating amount of heat absorbed or extracted by liquid vapor refrigerant, amount of heat is being absorbed from the surrounding is the refrigerant heat. That is RE, which is given by H1 minus H4, as shown here. This is the refrigeration process. The heat is being released here. H1 is the heat energy, heat content at the point 1, and H4 was the heat content at the point 4. And it is being, this difference is the amount of heat absorbed from the surroundings of the at the time of evaporator itself. That is the respiratory effect. Now, there is a point, that is a one thing, HF3, which is equal to which is equal to H4. What is HF3? So this has become R1 minus H4, and H4 is replaced by the term HF3, means enthalpy of the fluid of fluid refrigerant at point 3. So this H4 is replaced by 3 in the condition that this is a sensible heat at temperature T3, and the enthalpy of the liquid refrigerant leaving the condenser itself. Why we are using as well, first of all, this is said here. Enthalpy HF3 means here HF3 is equal to HF4. H4 means the enthalpy or heat content of your refrigerant at the exit of the condenser itself is equal to the heat content at the refrigerant at the entrance of the evaporator itself. This is exactly lying on the refrigerating line. This the low liquid vapor line here. So this HO3 is readily available from the psychrometric chart or from the steam table itself. So these 4 we can readily know which is the inlet pressure of H1, and 1 is also which outlet level of the evaporator itself. So it is noticed that in the cycle, liquid refrigerant is extracted heat during evaporation, work done by the compressor or isentropic compression of the high pressure and temperature, high pressure and temperature vapor refrigerant. So coefficient of performance COP is equal to output by input. Refrigerant effect is the output. What we are getting from the system is H1 minus H4. What is the work done from the system is H2 minus H1. Hence, the heat added in the compression process, which is in terms of what can be converted into the work done by the compression, which increases the heat content from H1 to H2, and the refrigerant effect, which is being done by the refrigerator itself at the time of evaporation by increasing the heat content from H4 to H1 itself. Thus, which is H4 is equal to HF3. So this is the equation for enthalpy of the system. I mean the CFP of the system. The ratio of the CFP of the vapor system is the ratio of Carnot cycle, sometimes known as refrigerating efficiency or performance index. It can be used in some type of some problems here. Just 1 second. Now, let us go through some problems here. What is given here? Just I'm telling you from the book. In the first problem, what we have, let us draw these two charts first. The temperature T, and this is the entropy, say S. There are two lines. P, H, and P. Here, so this is all trivial, which was shown in the book itself. That is one to two compression process, which is supposed to be vertical in PS diagram. There is no change in entropy. 2 to 3 is the horizontal line, and which shows that the entropy is changing from 2 to 3, which is heat is released here. 3 to 4 is the expansion process, which shows that entropy is to a certain extent increased as it's totally it is not totally isentropic process, and 4:1 is the evaporative process where enthalpy here is increased from 1 to 4 to 1, as well as entropy is increased from 4 to 1, which shows that the heat transfer takes place in the evaporating process. Here, heat is being transferred outside the atmosphere, and 4:1 heat is being transferred to the heat is being absorbed from the surrounding medium. Let us go through one problem before we finish quickly. Now, what we have a ammonia problem. An ammonia vapor refrigeration system. The pressure at the air evaporator is 2 bar. So here pressure at evaporator which is equal to pressure here, that is P4, and PV1, which is same. P4 is equal to P1. So P4 equal to P1 is equal to 2 bar. Now, during compression, the work done per kg of ammonia is 150 kilojoule. During compression, so here compression is going on from 1 to 2. The work is supposed to be done, which increases heat source here. So from 1 to 2, the H2 minus H1 is given by 150 kilojoules. Since this is the amount of being done by the compressor itself at the time of this cycle. Now, what we are supposed to do, and rate of ammonia cycle is rate of the circulation of the ammonia is 4.5 kg. Rate of circulation is 4.5 kg per minute. Just 1 second, please. Now, what we are supposed to calculate is the latent heat or latent heat of latent heat of the vapor of refrigerant is given as 1325 kilojoule per kg, and rate of circulation is 0.58 kg or meter cube per kg. So what we are supposed to calculate the COP and volume vapor intensity compressor per minute. Calculate COP and vapor volume of vapor intensity compressor per minute. Volume of vapor entering the compressor per minute. Now, another thing is given, ammonia at the time of at the pressure the ammonia exists is 0.85 also dry. So another thing is given, X1 0.84 is given, and X4 0.19. This is the dryness fraction. Which tells us the vapor is at the point 1 is dry by 84% and wet by only 0.16%, and at the point 4, it is dry by only 19% and wet by only 71% at the entrance of the evaporator itself. So dryness factor at here and here is also given for our consideration. Now, it's not about the pH diagram. First, we have to find out what is enthalpy at the point 4. Point 4. So actually, to know the COP, this equation is supposed to use, which is given as H1 minus HF3 divided by H2 minus H1. So what is H4? HF3 enthalpy at the point 2, that is H4, that is HF2. Okay. So how we are supposed to do it? What is given is rated heat of refrigeration, which is given as 1325 kilojoules per kg. So we have to multiply it with the brightness fraction here at the point 4, that is 0.19, 0.19 into 13.25, which is given as 2.251.75 kilojoule per kg. Now, why we are using the fraction like this? That is the most important question we have to understand. First, we have told you it is given that the dryness fraction at the point 4. What is dryness fraction? Dryness fraction means fraction is equal to the amount of vapor present of refrigerant present in the mixture of mixture of vapor and liquid refrigerant. So, or amount, or you can say percentage of vapor present in the mixture of vapor and refrigerant. So, if the fraction is only 19%, so the total heat of latent heat of vaporization is 1325. Only 19% of is vaporized. So, at the time of 4, only 19% heat is being absorbed from the surrounding itself. So that's why if we multiply 1.5 with the latent heat of vaporization, we'll get at 0.15 kilojoule per kg of vapor itself. And similarly, at the point 1, where and H1 at the enthalpy at the point 1, where the vapor dryness fraction is 0.85, which is multiplied by 1325, which is given by 1126 1126.25 kilojoule per kg, which means at the point 1, 85% vapor is being vaporized and only 15% vapor, only 15% liquid is not yet vaporized. So here we are saying that, so we can say that if, as 85% vapor is vaporized, so 85% of the latent heat is being absorbed at the point 1. So H1, or the heat content at the point 1 is obtained by multiplying the latent heat of vaporization with the brightness fraction given at the point 1. So we got the enthalpy at point 4 and got the enthalpy at 2.1, which means we get the refrigerating effect we got the refrigerating effect equal to H1 minus H4, or H1 minus HF3, which is given by 1126, this one 1126.25 minus 251.75, which is equal to 874.5 kilojoule. The work done during the compression is equal to, now we know it's what is given the work done during compression is given by, which is 100 for 150 kilojoule per kg. 150 kilojoule per kg. So COP is given by RE or RE by W. RE is here. This is RE and this is W. This is equal to 874.5 divided by 150. This is given as 5.83. 83. Next is vapor of the amount of vapor entering the compression. Next part of the problem, amount of vapor entering the compressor. What will be that? Should be equal to compressor per minute. This should be the mass of the refrigerant and specific volume of the refrigerant itself. The mass of the refrigerant and multiplied by the specific volume refrigerant coming per minute and is multiplied by specific volume means the amount of the volume of refrigerant coming in per kg, that is given here as MA is given as 0.45, 4.5 here. Rate of circulation is 0.45 kg per minute, and rate of 0.45 and rate of circulation specific volume at 2 bar. Not rate of circulation, this is given as specific volume. I've written wrongly. This is the specific volume. And 4.5 multiplied by 0.58 multiplied 0.58 usually becomes equal to 2.61 kg meter cube per minute. Now, so this is the answer we are getting. What we have here, first of all, what is given? It is told that it is the ammonia vapor refrigerant per cycle, and pressure of the evaporation is given. Pressure at the tap at evaporation is given P4 is equal to P1 is equal to 2 bar. But this pressure don't have any use here. Next is H1 minus H2. Then means enthalpy change from 1 to 2 at the time of compression from 1 to initial from H1 to final from H2. That is H2 minus H1 is given as 150 kilojoule per kg. And the latent heat of vaporization is given as 1325 kg kilojoule per kg itself. The specific volume is also given. So what we have calculated first, we have to calculate the refrigerating effect, which is not known to us. So you have to calculate H4 as well as H1 itself. What is given here, that latent heat of vaporization of this refrigerant, and we have decided as the dryness fraction at 4 and at 1 is given, the amount of heat added or at present in the refrigerant itself is the fraction of dryness fraction multiplied by the enthalpy for H4 and dryness fraction multiplied by enthalpy at H1. Thus, we got both this value of H1 and H4, and thus we have got refrigerating effect or the amount of heat being extracted from the refrigerator. So, as the work done with the compressor is given, so CF is the refrigerant effect divided by work done, and that is equal to 5.83. The amount of refrigeration to compressor per minute is the mass of refrigeration is the mass into specific volume. Both are given, so it is equal to 2.61 meter cube per minute. Let us go for the next problem. What is the problem? Here we are given the pressure, it is a refrigerant is ammonia. That is ammonia. The temperature limits of an ammonia refrigerant system is 25 degree to minus 50 degree, which is given temperature limit, higher temperature. That is T2 equal to T3 in our chart, which is given as 25 degrees centigrade. So it's equal to 25 plus 273 or 298 degree Kelvin. And the lower temperature of the system is equal to T1 equal to T4 is given as minus 10 degrees centigrade, which is minus 10 plus 273 is equal to 263 degree Kelvin. As both T1 and T2 are considered in Kelvin. And what are the other things are given? That is H4 is equal to HF3, which is given as the latent heat at higher temperature, which is 25% to 98 degrees centigrade, because